Hello and welcome to T3 Day 25 of Honors Precalculus. We will be talking about sequences and series. A sequence is an ordered progression of numbers, so the order really matters. So here's one example. You have 5 numbers in order here, and this is finite because it is non-infinite. It has a beginning and an end. It has an end. So here's another one here. This is an infinite sequence because it goes on forever. You have the dot, dot, dot here, means keeps going. And also it has a definition for each entry, 2 to the k. One way you can notarize each of these entries, this is the first one, so that's the A1, that's the A2, that's the A4, that one's A3, did a little out of order, but they go in order right there. These keep going here, and it tells you how to get each one. It's 2 to the k power, where k is the entry. So that's 2 to the first, 2 squared, 2 to the third, and then it keeps on going. And this is, k is a positive integer. And it's infinite because it goes on forever, and you know that because of the dot, dot, dot. Here's another one where it's just 1 over k, where k is 1, 2, 3. So if you wrote this out, it would be 1 over 1, then 1 over 2, then 1 over 3. That keeps on going. And sometimes you just abbreviate a general infinite series, A1, A2, A3, A4, dot, 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 like that. And that's infinite because of the 3 dots at the end. So for this one, let's find the first 6 terms and the 100th of the sequence ak, where ak is equal to k squared minus 1. So if k is equal to 1, you have k squared minus 1. So a to the ak is equal to k squared minus 1. So what you do is you put 1 squared minus 1. So 1 squared minus 1 is going to be 1 minus 1 is 0. So that means that when k is 1, you get 0. When you plug in 2, it's going to be 2 squared minus 1 is going to be 4 minus 1. And if we continue this, you get 3. Next row and the next few would be, so there are your first 6 terms right there. So A1 is 0, A2 is 3, and so forth. You do it out carefully, it's not that bad. And these are explicitly defined because each term is defined independently, meaning I can plug in 2 and get the second term. I can plug in n and get the nth term. It's not dependent on knowing any of the other terms. So what would A100 be? A100 would just be 100 squared minus 1, which is 10,000, minus 1, which is 9,999. And the way you could write this is 0 is the first term, and then you end up with 3, 8, 15, 24, 35, dot, dot, dot. And you could write the general term. You could say it's equal to k squared minus 1 if you wanted to, like that. So another way we could define a sequence is recursively. And what's going on here is that each term is dependent upon a previous term. It could be more than 1, but in this case it's 1. So the first term is 3. So we know the first term starts at 3. So when a is when you have the first term, so that's b1 is 3, how do you get the second one? So let's say you wanted b2. This is saying it's equal to the last term, b sub n minus 1. So b sub 2 minus 1 plus 2. Well, that's just b sub 1 plus 2, and we know b sub 1 is 3. So that's 3 plus 2, and that's equal to 5. So then we know b1 is equal to 3 and b2 is equal to 5. What this is telling us is that it's the next term is always equal to the last term plus 2. So that means that b3 is just going to be the last term plus 2 is 7. So that's what we have so far. So then b4 is going to be 9, b5, you add 2 again, is 11, and b6 is going to be equal to 13. Now, this is recursive because it relied on the last term. So how do we find out what the explicit term is? Sometimes it's a lot of guess and check. You have to be really careful about it, and it can be very hard, but it can be very, very, very helpful. What this really means, if we wanted to find the explicit formula, is finding a function that turns 1 into 3, turns 2 into 5, 3 into 7, 4 into 9, 5 into 11, and 6 into 13. This is kind of pattern recognition. If you double each of these things and add 1, what do you get? You get the next term. So like 1 times 2 is 2 plus 1 is 3. So you double, if you study this, you double this and then you add 1. You double that and then you add 1. So you end up with the explicit formula, Bn, is going to be 2 times n, and this is plus 1. So for example, if we wanted the 100th term, it would just be 2 times 100 plus 1 is 201. And we wouldn't have to find all of the terms in front of it. Another way to do this is literally to plot these points and notice that it's a line. This is a linear function. An arithmetic sequence is a sequence with a common difference. You'll notice here there's a common difference. Goes up 2, goes up 2, goes up 2. So the difference is 2. This goes up 5, 5, 5. Difference is 5. So that's an arithmetic sequence. Each term can be defined recursively by the formula, the last term plus the difference, or explicitly by the first term plus n minus 1 times the difference. So the first term on the last one was 3. And then if you go back and look here, what was the common difference here? The common difference was 2 right there. So we can actually use this formula right here, plus n minus 1 times the common difference is 2. And if you simplify this, you get 3 plus 2n minus 2, which is just 2n plus 1, which is what we got before. But this is a formula we can use for any arithmetic sequence to get the explicit definition, which is very, very useful. Recursive is cool, but explicit is more useful in general. So let's find, for this sequence right here, it's infinite, the common difference. What's the common difference between all of these? Well, it's 4, so the difference is going to be 4. And then in recursive formula, so what do you do for this one? Well, an is just going to be the last term plus 4, where a1 is -6. You got to give it a place to start. This is the place you start. You got to give it a place to start or it doesn't really work. And then it's asking you after that for an explicit formula. For the explicit formula, so that's going to be an is equal to, where is it? The first term, -6, plus, what do we do there? It's going to be 4, the common difference, times n minus 1. Put the 4 in front, it doesn't have to be in front. And then fourth, it says find the 10th term. So a 10 is going to be -6 plus 4 times 10 minus 1. -6 plus 4 times 9. So -6 plus 36 is equal to 30. That's why the explicit, this is explicit and this is recursive. The biggest reason explicit is so useful is because you can just find a value really nicely. I don't need the first 9. Recursive, you would need the first 9 to get the 10th, but this one you just plug in 10. So let's do the same thing here. These are just numbers, and we do the same process here. So what's the common difference? Well, the common difference is you subtract the two things. So it's this minus this, or this minus this, and it looks different, but it's ln 6 minus ln of 3. And log rules state that that's ln of 6 over 3, which is ln of 2. And you're going to get the same thing. Like if you did it with the next two, ln 12 minus ln 6, that's ln of 12 over 6, which is just ln 2. So in this case, the common difference is ln 2. Next, we need to find the recursive definition, and that's just going to be the last term, an minus 1, plus the common difference, ln 2, where the first term we need to give is ln 3. That's where it starts. That's how it's defined. And then for the explicit definition, an is going to be, ln 3, the first term, plus the common difference times n minus 1. And then if we wanted the 10th term, that's just going to be a sub 10, and you plug it into the explicit, and you get ln of 3 plus ln of 2 times 10 minus 1. So that's ln of 3 plus ln of 2 times 9 right there. And the way you can simplify this, if you want to, is you can put that 9 in front, so it's ln of 3 plus 9 ln 2, and that turns into ln 3 plus ln 2 to the 9th power, and plus means multiplication, so you get ln of 3 times 2 to the 9th. It's a pretty big number. We end up with ln of 1536. So yeah, you got to remember your logarithm rules. The next type of sequence we're going to look at is the geometric sequence, where between each term there is a common ratio, meaning you multiply by the same thing to get the next term. So you multiply by r, you multiply by r, you keep on multiplying by r. And it's giving you a formula here. It's recursively, the nth term is the last one times r, and explicitly by the first one times r to the n minus 1 power. So these two are very powerful tools. So for example, we can use them. I'll leave that right there. First, it asks for the common ratio. Well, that's 6 over 3, which is the same thing as 12 over 6, which is the same thing as 24 over 12. You can assume it's always going to be the same. You don't have to do all three of them. So the common ratio is just going to be 2. For B, it's asking a recursive formula, so that's just going to be an is equal to an minus 1 times the common ratio, which is 2, like that. You just multiply the last one times 2. Relatively straightforward, but then you have to say a sub 1, where does it start, is equal to 3. But then C, what's the explicit formula going to be? That's a sub n equals the first term, which is 3, the ratio to the n minus 1 power, and then D is the 100th. So 10th, sorry, a sub 10. So that's going to be 3 times 2 to the 10 minus 1, which is 3 times 2 to the 9th, which is 1536, which you might remember from the last problem. So again, it's the same process no matter what the number types are like. So for this one, the common difference is 10 to the negative 1 over 10 to the negative 3. And that's 10 to the negative 1 minus negative 3. So that's 10 squared. So that's our common ratio, which is just going to be 100. So you multiply by 100 to get each of the next terms, but times 100 to get the next term. So for B, it's the recursive, so that's going to be a sub n is the last term, a sub n minus 1 times the common ratio, which is 100, and the first term is 10 to the negative 3. And then the explicit formula is going to just be 10 to the negative 3, the first term, times 100 to the n minus 1. That's the ratio to the n minus 1 power. So then D, what would a sub 10 be? This is where it comes in handy. It'd be 10 to the negative 3 times 100 to the, to the 10 minus 1. So it's going to be 10 to the negative 3 times 100 to the 9th. And you can simplify this. 10 to the negative 3, 100 is 10 squared to the 9th. So that's going to be 10 to the negative 3 times 10 to the 18th. You add them and you get 10 to the 15th. So yes, you need to know your powers. And this is the last big idea of this page, which is a sequence is said to converge if as n gets big. So as you go infinitely to the right, as n gets really big, an goes to a finite number L. Otherwise, the sequence diverges. So what I mean by that is if you list these out, so if we list this out, n is 1, then 2, the first term is going to be 1 over 1, then 1 over 2, then 1 over 3, and then 1 over 4, and then 1 over 5, and then it keeps going here. As n goes to infinity, what does this go to? Well, it gets to infinitely close to 0. So we say that this converges to 0. But what about over here? N is 1, you get 2 to the first, and then the second one is 2 squared, and then 2 cubed, and then 2 to the fourth. Is that getting close to a finite number? No, it's getting infinitely big. So this one diverges. It doesn't get close to a finite number, but this one, not I, converges. What about this one? Plug in 1, you get negative 1 to the 1. Next one, negative 1 squared is just 1. Then an odd power, then an even power, then an odd power, then even. Does this converge? Does that get infinitely close to a finite number? It does not. This thing bounces back and forth, so we say it diverges. And this is a big thing we're going to look at. Do sequences converge or diverge? We're going to do a lot of that.